first thing is that I should have added one more name in our collaborators, that is Babar Qureshi from Lahore, whom some of you may know. And on the gravitational part, there is a paper in the net now. Now I should start by, please switch off the light.
We want the light.
Where is the light?
That one.
No, you switch off. No, so switch on. Okay, he wants.
You want that light? Which light do you want?
Which
I want to write on the blackboard for a few minutes, then switch it off.
You don't need this light, right?
I want the light so that people see what I am
No,
writing.
we can't. It has to be the entire thing. It can. We can't have a
First three lights.
focus.
Yes, put it on.
That one? Will that?
Put on everything, isn't it?
Okay.
Okay.
He wants to put on everything.
Okay. So, I want to start by outlining, first telling why I am talking about dark radiation in gravity. What does it mean? Okay. So, the title is coming because literally in quantum gravity, what I want to argue or rather show is that we know that the energy in all the conserved quantities in an asymptotically flat space-time reside at infinity. Okay. That is, so it is, they are usually presented as surface integrals, and what I will show you is that because of infrared effects in quantum gravity, what happens is that this energy gets shifted. Okay. And I will show you the calculation. Okay. It is quite a concrete calculation. So I will show that the expression for the so-called ADM mass, which is written in the form that 8-bit wrote using spinors, gets shifted because of infrared corrections in a calculable way. Okay. We have made estimates of what the shift is. Okay. But the effect itself traces its origin, the calculation itself traces its origin to another effect with which many people seem not to be familiar, but although it is quite ancient almost, it is almost 25-30 years ago, and that is the fact that in QED, because of the infrared effects, Lorentz invariance is spontaneously broken. This was first shown, research in this direction were accumulating for quite some time since the 60s, and eventually it was proved by, from my knowledge, first by a person called Ropstoff, and eventually at a high level of rigor by Froelich, Murchio, and Stropke. And I will show you the reference as we go along. So, how does that happen? So, since I definitely will not have enough time to say much, okay, so I'll outline what are the kind of things that happen. Okay? So, normally, if you do perturbation theory, what one starts with is, for example, if you want to have a charged particle, then suppose you have several charges, several particles of total charge Q and total momentum P. So it may be that this is composed of several individual momenta. So I suppose I take it in the Fock space, and I take the vacuum of the photon in the Fock space. So this is the Fock space vacuum, and this is the normal scattering theory will take this object and ask what is the in-state. Okay. But normally, so what you apply is a so-called Euler operator to this Fock space state, and you call it the in-state. Okay. And nothing very dramatic happens. You can calculate it if you have a massive particle system, everything is, at least, there is no infrared divergence associated to it, and we do this calculation all the time. For example, if you do LSC formulation, this is what we do. But what happens in QED is that this object here is some vertex operator, which depends on the total charge and the total momentum, and acting again on the Fock space space. By Fock space I mean this object, so the particle and the photon, and this vertex operator is the one that dresses the whole system. And what happens is that this operator takes you out of the Fock space into a non-Fock space. Okay? And what you find is that this object here is not living in the Fock space. For example, the number operator of the photon in this space diverges, and even more dramatically, and I will show you as we go along, even the boost generated diverges when you evaluate it on this state, and consequently you have a spontaneous breakdown of Lorentz invariance already in QED. Similar, no, this is because of infrared effects. Similar things happen actually also in QCD, but I will have no time to talk about it here. But in particular also in gravity, where instead of the photon which is dressing here, what I have used in my calculation is the spin connection, because the matter, for example, the particle, say spin half particle field couples to spin connection very much like as it does in QED, and since I am only interested in low frequency modes, so I am only interested in asymptotic regions where I am assuming asymptotic flatness. You can use the QED results, treat it as a flat space for very low frequency modes, and you again get a result of this kind. And then I can calculate how the ADM energy shifts. So that is what I will apply to do. And no local experiments can detect it either, because this is something which is surrounding the system. So depending upon the scale of the problem, it is not accessible to local experiments. So I decided on the phrase that this is a dark energy. The full consequences of this result we have not appreciated, I would say. So there are similar shifts in momentum, and
This
also
is not the same dark energy which is used in cosmology.
I do not know. This will be a contribution to that, but how much it is, I do not know. What are its properties, I do not know. Okay? So it will definitely be a contribution if that dark energy that people are measuring is in comparison to the ADM, the short standard ADM mass. Okay? So we have a massive body, and you say it has mass m, then this will be, it will not be of mass m. In the quantum gravity, it will be shifted. So it will be a contribution to the dark energy, but what does it have the correct properties? There are many questions you have to ask. What fraction is it?
But that may be right, but dark radiation is again a technical term used in a particular
So we have to find the
in
particle.
the brain world.
It's a local effect.
Brain world, let's not talk about brain world, please.
No. I mean, is your dark radiation. This phrase
Yeah.
is used for in technically in the brain world thing, where from the bulk what gets projected down on the brain is called the dark radiation, because there the radiation is only means that it has something which has trace zero. It's a trace free thing. But anyway, it's only that you are just using a.
Dark radiation, I am using it, I think, in a good physical way, and I change the phrase by saying from dark energy to dark radiation, because I do not know that dark energy is composed of just this. Okay? But what I am sure is that this is a contribution to the total dark energy. Okay?
But this dark radiation, will it have negative pressure?
That so far as I am concerned, no, I have not. First, I am not competent to investigate that issue. But so far as I am concerned, you can cover that by putting the cosmological constant. No, so far as I know. Yesterday somebody asked this question to me. Maybe I am wrong. But what I know is this: if it exists,
So let us go ahead. Forget about the
what are
name.
its detailed properties, I do not know.
Yeah, that's okay. Let us see. Let's see what.
Okay. Now, towards the end of this talk, if there is time, there has been some very striking and beautiful results in the theory of quantization of fields in the curved backgrounds. Okay? And there are very striking and very rigorous results where you start with the assumption that this is a correct assumption, that you do not really know what nature is like outside some compact space-time region which I will call M. You do not know what happens outside. So you are only given, being human and hence limited, we only know what is, maybe even that approximately, in some finite space-time region. We don't know, maybe the metric we are given in M, if you try to look what it looks like outside, it has closed time-like curves, or it is something completely non-differentiable. We do not know. Okay? So, question that people have asked is, given this limited information on M, can I create a quantum field on this limited space-time M? Okay? This is a very relevant physical question. For example, it can be applied to many situations. For example, for the FRW metric. Okay. Now, this question has been answered. Okay. The first answer is towards this direction came from the people working with white, people like Wald and Wirch and not Wirch, Hollands and Wald and many others, and they create all the correlation functions with this limited information using what are called Hadamard states. So they describe what it is. I will not talk about Hadamard states here, but in particular there is a generalization or another approach which is quite easy to understand due to Sorkin and Johnson. So the Sorkin-Johnson approach is again an alternative approach to this idea that knowledge is limited. Okay? So to talk about all over the universe and talk about create the vacuum state, which is the most non-local object you can ever imagine, okay? Where you need the data of all of space and time. Okay? You cannot, I mean, normally if you take books, they are trying to create creation and elimination operators back. That looks absurd because you do not know what happens outside. And this construction does not require even that the metric has a time-like killing vector, even in M. Okay. All that it is necessary is that M is globally hyperbolic. Okay. So, given this statement, the quantization can proceed completely covariantly, you get an answer, and that answer in the specific case of say Minkowski's case, when M goes to infinite volume, you do recover the standard quantization. Otherwise, you have a quantum theory in M. But I will not use phrases like ground state, but the correlation functions are related to, the correlation functions are all given, but they are given related to some state which one should not call the vacuum. So you have all the correlation functions related to some state, but I don't know what is meant by vacuum because there is no Hamiltonian. There may not be any time-like killing vector. But once I am given all the coordinates, the quantum theory is completely different. Okay? So this has been done, okay? And people have been discussing it. And if there is time, I will mention it.
There are of course space-times which are not globally hyperbolic.
That
Yes, for instance.
Huh?
De Sitter has.
but there you put the
So
special.
does will M extend up to the quotient horizon? Is that what you have in mind?
No, you give me a space-time region.
Yes.
ADS is, that is, so some fake calculations go on. ADS is not globally hyperbolic.
No.
So there is a problem because information can go out.
Right.
Then they do all kinds of
And
things.
come in, yeah.
But that is not an activity I do. That is an activity that people who want to do ADS CFT correspondences sort. I don't do it.
Okay.
So, I don't do it because I think I don't find it, I don't know what's going on there. Okay? But here I am saying that give me a bounded space-time region M where the metric is given with the signature with 1 minus and 3 pluses or 1 minus and 7 pluses, I don't care, which is bounded, and this M is globally hyperbolic. I do not require that, G has a time-like killing vector. I do not, but M must be globally hyperbolic. Then you can write down the full quantum theory in M. Okay. So, and you can find all physical questions, you can answer them because all correlation functions can be evaluated. Okay.
Okay.
So, this is my,
15 minutes.
yeah, I have already taken up 15 minutes, so I will say what I can, but instead of hurrying.
Right.
Now, I need the,
Pointer is there.
how do I change it?
This.
Right.
Okay. Huh?
Except with this.
Okay, okay. Okay, so I start with this very beautiful quotation, okay, which was gifted to me by Amilcar, okay, coming from Carl Gustav Jacobi, okay? You can see that he was a spirited person, attacking of all people Fourier. So calculating numbers is not our primary activity, but to absorb the reality of nature is, I think, what I understand by it. Okay, let me go on. So the starting thing is, I want to remind you of very elementary results regarding quantum mechanics. So, and in particular, the so-called Weil algebra, which is more appropriate to discuss quantum mechanics. So, what is a Weil algebra? So, I start with a case of one oscillator with position with A and A dagger, where Q and P are Q hat and P hat are position and momentum operators, standard commutation relations, and we introduce this complex variable Z. Then the Weil algebra, so-called Weil algebra, is defined by this W of Z. W is standing for Weil, and it is labeled by a complex variable Z, and it is defined by this equation. Okay? And this is the same after you normal order it to this operator. The advantage of this operator over A and A dagger is that this W is unitary, whereas A and A dagger are unbounded operators, and very quickly in non-trivial issues, for example, when I start discussing scalar fields, you get into troubles or you get into difficulties of divergences by multiplying unbounded operators. Okay. Now this W fulfills this equation by just applying standard rules of Baker-Campbell-Hausdorff formula. You get this equation. Okay. But this object here is I times, if I separate this Z1, Z2 into Q1 plus IP1, etc., you get this equation. And you see that this is antisymmetric in the 1 and the 2 symbols, and it is this antisymmetric form is actually a symplectic form. Okay. Up to the I, it is actually a symplectic form. Okay. Now, we can define in the sense of a density matrix, or in the sense of a state in an algebra, we can define an omega 0 by saying that on Wz it is equal to this. Okay. But if you want to write it in terms of vector space, this is the same as vacuum expectation value for W. This is well known, and I am using the fact that the vacuum is annihilated by the annihilation operator. So this is now it is a fact that you can start from this equation here. Not worry about where it came from, but start here, and there is a canonical construction called the GNS construction, which enables you to recover the full Hilbert space, and also the fact that full operator realization of W as acting on a Hilbert space. And this is more relevant or more important when you go into quantum field theory, when I start talking about inequivalent representations and so on. One point to notice is the number operator preserves this omega 0. That is because the number operator changes the phase of the complex variable by IT, and that cancels out here. Okay. Now, what I want to tell you in the next few minutes is how to change this state. So I will instead of W0, which was defined by, how do you go back now? Omega 0 was defined by this equation, saying that omega 0 and Wz is this one. Now I want to change that. So I say that omega of F is on W of Z is omega 0 W of Z, which I know already, times this extra factor here. But this F here is linear in the variable Z. So it is a linear functional on this Z. This will define a new state. What is this? In terms of standard quantum mechanical states, I can write that down by a well-known theorem in Hilbert space theory called the Ries-Fischer theorem. Okay? Ries-Fischer theorem, I believe. Any linear function like this can be written, f of z can be written as the scalar product of z with a psi bar. So it is a scalar product here of psi with z, and I can write this omega f as, so given this fact that I can write this here in this way, imaginary part of this one, you check that this omega f of Wz is exactly this expression, where the vacuum state has been twisted by this W psi. W psi is the where is it?
Middle.
Yeah. W psi is, the Z here is replaced by psi. So what I have done here is to show you that I have created the quantum theory starting from a coherent state. It is given by this W psi. It is labeled by psi and psi bar. Okay? And it is built from this density matrix of this state here, and by a GNS construction you recover the full Hilbert space. Okay. Now let me apply this idea to a quantum field. For a quantum field, I can go to a certain extent in the same way. The canonical commutation relations are given by this equation, and again I need an A and an A dagger, which is introducing what people call as a complex structure. Namely, I am putting an I am introducing an I, starting from a real field, but I am introducing an I. So I take a complex combination of phi plus I pi, which I call A hat. So this is an analog of the annihilation operator. But now I have to introduce the analog of Z, and for that what we do is we take a complex function f. Okay? The plus here I put to show that it is complex, but because at some time I will have to deal with real functions. So it is a complex function on R3 with values in complex numbers. So, and what I do is smear this A hat with this complex function. This is a test function of A hat, and I construct this operator. Okay. So this is analog of what we did with the complex variable Z. So the while operator for the quantum field will be constructed, written as again as a unitary with A dagger and A here, but smeared with A plus and A plus bar. And you can again normal order it and you get this. And you can also introduce a scalar product, which I will need later, between the F pluses. For the one complex variable scalar product is trivial, but here I have to tell you what it is. Okay? And the while algebra is looks exactly like what we had for a single particle. Okay? And this object again is an imaginary part up to 2i. It is F1 and F1 and F2 are real parts of F plus, real and imaginary parts of F plus, and this is antisymmetric and G similarly, and this is antisymmetric in F and G. It is in fact a symplectic form governing the theory. So how do I write the Fock space? Well, the Fock space is written exactly as in quantum mechanics by saying omega 0 and W of F plus is this expression. So give me this, I can recover all of the Fock space participation of the scalar field. In case
this compact space
F plus is F plus is normally, I will come to that exactly. F plus is compactly supported, but the crucial point is that F plus is square integrable. Okay?
So F plus, when you write F plus bracket,
It's a scalar product which I wrote down earlier. I have put a scalar product.
and it's
yeah, okay.
a differential.
Of course, I mean this three-dimensional scalar product because which is coming from the fact that I am writing this delta function here. Okay? This implies that the scalar product with which this delta function is acting is d cubed of x on spatial slice. So you get this scalar product. Okay? This is yeah. So before I had something very trivial. I had simply z bar z,
Yes.
but it is more complicated here. So now I want to twist this this omega 0. We will see that this twist plays a very important role in physics. So I will take a linear function f, which is taking this f plus to a complex number. So I am not going to tell you how I find this. This is a linear functional, and I will try to see how to write this linear functional in a suitable way. Then I will define a new state. Okay. which is given by this linear functional, which is the original one multiplied by this twist factor. Then this is a new state. If you want, you can go and check that the axioms of a state is fulfilled. Now comes the certain issues. Okay. Now I have already given you the scalar product here, which you can rewrite, if you like, in terms of the Fourier transforms in the standard Lorentz invariant form, in terms of the Fourier transforms. Okay. So I can write in the original way, or I can write like this. And the issue then is as follows. When can I write this scalar product, this linear functional as a scalar product of f plus with a psi, where psi is in this Hilbert space? Okay. So the question is, I give you a linear functional, but can I write it like this, where psi is an element of the Hilbert space? Then if it were, then I can say that I have a generalized coherent state with which I am working. Okay. Then the Ries, or actually Ries himself quotes Frechet also. Frechet-Ries theorem says that this is possible if and only if, okay, if and only if, okay, this linear functional is bounded. What does that mean? The supremum of this on all f plus, okay, which is normalized, is less than some constant. Okay. If and only if this condition is satisfied, can you write like this in this equation, where psi is an element of the Hilbert space. So, if psi is an element of the Hilbert space, what you can see immediately is that this the omega f I wrote down is equivalent to the vacuum expectation value of this W of f plus, but twisted by this W psi dagger. Okay. And W psi is an element of the Hilbert space. So what happens is that this, you are still remaining in the original Hilbert space, but you are working, instead of looking at vacuum values, but you are looking at a coherent state in the Hilbert space and taking expectation values. So you are not going away from the theory. Okay. It is the same theory, but you are looking at expectation values on some excited, I should say some coherent state, like in quantum optics. Okay. So nothing new happens. You just change the focus of attention to another new state. But suppose this is not true. Suppose it is the case that the linear functional you have defined is not bounded. Can I show you examples of this? Plenty. Take any psi which is smooth and infinitely differentiable, but which is not square integrable. Example, take a function psi which, as r goes to infinity, goes to some angular dependent limit at infinity. Okay. This is not square integrable. If you try to do square integration r squared dr on this, you will get infinity. Okay. However, this f plus, as he pointed out, is typically compactly supported. So this equation still makes sense. It is not square integrable, but this equation makes sense because f plus, for example, can be taken to be compactly supported. So this integral still exists. So the previous equation I wrote down in the previous page, in this page, this equation, this W psi with which I am twisting the omega is no longer an operator in the Weyl algebra, because the psi here is to get an element of the Weyl algebra, which will be of this W of f plus variety. This argument must be in the Hilbert space. Better still, it should be compactly supported, but that is not the case in this example. So you can write like this, but this W psi is no longer in the Hilbert space. This object here is not any longer in your Hilbert space.
Please remind us what is the state ket omega?
Is actually the vacuum.
But vacuum requires a Hamiltonian, right?
No, it just requires that the A operator, vanishes. There is no Hamilton. The role of the Hamiltonian and so on in this kind of description is something different. I'll come to that later. It is not part of the observable algebra. That is also the case in local quantum field theory, because maybe tomorrow we can talk. They are not part of the observable algebra, but they are automorphisms of the observable
So
algebra.
you require a unique state K omega, which is annihilated by A. Unique state, only one state.
That I am assuming. I don't know that, since I have not used Poincare invariance, you can assume that. I am not sure about
So
it.
is your omega different from the zero?
It is the same, it is just by notation, typo. Now, so the correlation functions I am building is now with 0, let us say, on which this W psi is operating. Okay? But since this is diverging, the number operator in this new state is infinite, because this W psi will go and shift this A and A dagger, but in fact you can calculate it and you get this expression and it diverges, because I told you that the Fourier transform diverges. So even from massive scalar field, you have now found a new quantum state and an inequivalent representation of the commutation relations. There are infinitely many of them. In fact, there are uncountably infinitely many of them, because there are zillions and zillions of this size which are not square integrable. For example, the particular angular dependence at infinity I can choose in any way I like. Okay? For each such choice, I get a new representation. Okay? So there are a huge number of inequivalent representations in quantum theory,
Quantum field theory,
quantum field theory.
not in quantum mechanics.
In quantum mechanics, unless you have boundaries, then the story. If you have boundaries, then the story again changes. Okay. This I don't want to do that. I want to just spend very quickly. Okay, my whole idea is to generalize this to quantum electrodynamics. So here I have to tell you how do I get the Weyl algebra. A convenient way of writing the Weyl algebra is following this Roth-Stoff. So again, I need test functions, because because quantum field, not a philosophy. Quantum field is not a function. Okay? Quantum field is some operator value distribution, and you have to tell what the distributions are. To say quantum field as a value is not very meaningful. Okay? If you're doing classical physics, that is different. Okay? But quantum physics is, I think, much more subtle than classical physics. Okay? Much more difficult also to comprehend. So I have to tell you the test function space. In the canonical test function space, we choose to create the Weyl algebra will be test functions which are infinitely differentiable and of complexable. And it is convenient to choose them to fulfill the Lorentz gauge condition. Then I can construct this A by smearing this A given operator with F. So I am using this operator, local operators, as a trick to find out the Weyl algebra, and then the expressions I wrote down were in space-time. Yeah, I am writing the whole thing in space-time to get a more covariant way of writing things. The reason actually was also Sorkin thing. Then the commutator of two of these fields is given by this expression here, where this D is a causal commutator. I will.
This is in flat space time, right?
I am only doing flat space. Sorkin Johnson, I can tell you how to do it in curved space. So this is the causal commutator, which is the difference between the retarded and advanced commutators. Okay? And you can write down the Weyl algebra. To save on time, let me keep going, okay? Because there is some scalar product, and now given this Weyl algebra, there is some scalar product which is given by the Fourier components of f. Basically, you can extract from the Fourier components of f, which has 4 indices, something fulfilling the Coulomb gauge condition, okay? And you should be square integrable. Okay? So I will skip the details because I have not enough time. Okay? And the Fock space is given by this expression here. Again, I can twist this space, Fock space, to something new by putting a linear functional f on this test functions, where this f plus is the eta data I was writing down. Okay? And if you do that, you can keep going exactly as previously, and you can write down this W psi, and it is twisting this state here. And what happens is that you can compute this W psi, and it turns out in terms of the original creation and annihilation operators as the positive and the negative frequency parts of psi. So positive frequency parts of psi mu multiplies A mu minus, and psi minus multiplies A mu plus. Okay? And what happens is that if psi is square integrable, okay, so if this linear function is bounded, even in this vector case, then if that which is the same statement as this saying that the Fourier components of this psi are square integrable, then this W psi acting on the vacuum is again in the Fock space. Okay. So you are creating a coherent state of photons in this case, but you have not done anything new because you are staying in the Fock space. So this is unitarily equivalent to omega 0. So next thing I want to tell you is what happens if I have a charged state of, as I started at the beginning. Take a, I'm only interested in infrared radiation. So take a free charge state of total charge Q and total momentum P and call it this one. Okay? This may be composed of many constituents that is not relevant at this moment. And I take the photon vacuum. Then the yield state in scattering theory is obtained by applying this Møller operator, which is this operator acting on the Fock space state. You can calculate it. It is a standard time-dependent perturbation theory calculation, and you can calculate it, and you get this expression. But this V omega is a vectix operator, which is replacing this W psi now explicitly. Okay? So I can calculate what it is. This is what I call W psi, but now this omega, this psi is labeled by omega. Okay? And this omega that comes here, the issue is whether it is square integrable. Well, you can find, you have an explicit expression. The omega, Fourier transform of omega is given by this expression. And P is the total momentum, K is the frequency of the photon, and Q is the total charge. And it is transverse because you project out a transverse component from this omega. And lo and behold, if you compute omega omega, you get infinity. So this object is not square integrable. By the way, all the Weinberg's theorem on soft photons is obtained by expanding this in a power series. And so what I have done is to sum the whole thing. But expansion in power series of a vectix operator twisting between inequivalent representations is to me highly questionable. Because it is something which is going from it is going to inequivalent representations. Then you are doing perturbation theory on it. It seems not correct. Okay? In particular, that kind of activity will miss the fact that boost is broken, which was proven by Friedrich Mortev's thought. How do I prove it? They are given very strong arguments, detailed arguments, but I will give you a quick answer. Well, first is you can check that the number of operator diverges. Okay? The number of photons in this crystal state is infinite. By the way, there are no renormalization or anything. This is not a problem of renormalization. This is not a problem of loop divergences and you have to put cutoffs. It is not that problem. Okay? It is a problem of the fact that photon is massless. Okay? That is the issue that is involved here. So I compute. There are many ways to show it. The issue is whether, it is not the issue of whether I can implement the Lorentz transformations or Poincare group as automorphisms. To take the Weil algebra, the underlying algebra is Weil algebra. That admits Poincare group as an automorphism group. Then you can apply by hand Lorentz transformations and you will get an isomorphic. It will map the Weil algebra to itself, okay, fulfilling all the relations. Now the question is whether that Weil activity can be unitarily implemented on the quantum states. And the answer is no. There are many cases where automorphisms cannot be unitarily implemented, and that is the case here, because if you take the boost operator in canonical theory is the square of the electric field and the magnetic field squared, and now this is getting sandwiched between V dagger and B. Okay? So in the standard vacuum, this V and V dagger are not there and K will annihilate the Fock space vacuum. But now you have V dagger and the V, So what it does is to shift this E by this omega. This whose Fourier transform I gave you, and it gives you the frequency distributions. Fourier transform gives you the frequency distributions of the photons in the low energy element.
3 minutes.
Yeah, I'll finish. So this is divergent because this omega squared, omega goes like 1 over x squared. So omega squared goes like 1 over x to the 4th, and there is a d4x. This logarithmically diverges. So boost is spontaneously broken. No, I have 5 minutes. I started 45 minutes.
Okay.
I started. And that I know.
I am the chair.
Oh,
Forget it.
I started at 12. It is 12:40.
145.
Hi Hitler.
I don't care. I'll do it.
So let me finish off with gravity. The dominant vertex operator is this object here. Okay? So what I want to tell is that even in quantum gravity, I am only interested in the asymptotically flat region, but very low frequencies. So it is very probable that we know that if I put matter in the gravitational field, say of some massive particle, say spin half particle, it will couple to an interaction like this. So, it will couple to an interaction like this in the Lagrangian lattice. Okay? But the covariant derivative is with regard to the spin connection. So now this expression here, the spin connection here, asymptotically from very low frequencies, where I am in the asymptotic region, certainly by classical estimates, but for all from all intuitive reasoning, it will become like a flat connection. It will become like the connection of electromagnetism, because the spin connection here is living in SL2C, and asymptotically only if you look at estimates of what it happens, it becomes a UL connection. I think he also has used that in a great way. So there is good reason to expect that this is what is happening. So I am saying here that this A, I will finish very quickly. So I want to write this vertex operator for all x, at least to do some calculation. So the connection I will put here, it will be the self-dual connection, for the reason that the Witten, because I know how to commute that with other objects, and ADM energy has been written using self-dual connections by Witten. Okay? So I am going to use that. Okay? It is quite convenient. And this A is self-dual, as I told you. Okay. So I will finish here. Now, main point is, why did I choose the self-dual connection? The commutational relations of the self-dual connection with the electric field, their algebraic relationships are quite simple, and they are known. Okay. They are known by many people, Abhay Ashtekar, many people, also our friend here. This is known. It is quite simple to handle. Okay. And I am only focusing on asymptotically flat spacetimes. Okay. Now look at the ADM energy. ADM energy in the Witten language is this expression here. It is written as a surface integral at infinity, and there is some I over 2 pi g, I forgot, and there is a gamma phi, but never mind. So, and this spinor psi is a constant spinor at infinity, okay, which is normalized to psi diagonal psi equal to 1. Okay. Now, by assumption and by some calculations we have done, because if there is a massive particle of the kind I have written down here for spin half, it will start radiating exactly as happens in electrodynamics, and you can sum them up, and you can see what happens. And the twisted, what is it? The dressed state of the massive particle is getting dressed by this vertex operator. By this vertex operator written down here. Okay? So, but I can calculate so I have to sandwich the ADM energy, this expression here, between two states which are twisted by this vertex operator. So this is acting on, say, the state of mass m for the ADM mass, and this V dagger will sit on both sides of ADM expression, and if I know the commutation relations of V inverse EV and V inverse A V, then I can calculate how ADM energy has been shifted. Okay? Okay. And I also know what is the asymptotic values of E and A, but they are all known. Okay? Asymptotically, A classically is given, for example, in Witten's paper is just this. Likewise, the frame becomes a unit frame at infinity, and I know how the V transforms A to some new value, so we can calculate how the ADM energy shifts. We have calculated it, and the ADM energy definitely shifts. ADM energy density definitely shifts. Okay? We have made some estimates, but there are some unknown constants which appear in the estimates, so I cannot control. At this moment, we do not know how to control it. But the issue of whether it gets shifted is unambiguous. It comes like that. So, what I want to stop here is exactly the right time. We have computed this. I have not computed how the momentum gets shifted, but it is very easy to do that. Okay? Because all that I have to do is compute FTAG this expression, and similarly for the V inverse AV using the commutation relations which I already know. Okay? Then see what happens. Okay? Only asymptotically I need to do the calculation, and we have done it. And all these things get shifted. So ADM energy gets shifted. So if you have a particle of mass m gravitating, and you assign say solar, but it is going to get shifted by energy which is quite far away. So presumably it is like dark energy. What is this? What fraction of the total dark energy it is? I do not know. So we call it dark radiation.
Is it a positive shift?
No, energy density can fluctuate between positive and negative values. Okay? It does not. It is oscillatory at infinity. See? So even that is not true. Okay? But anyway, this effect is there, which is what I wanted to say, and I'll stop here.
There is a good friend, 2 more minutes. Now, questions.
So, but what is, get me the record. What is this shift due to? What is the physical thing which...
Because the massive particle is going and it is emitting infrared gravitons.
The infrared gravitons at infinity.
Actually, a spin connection. Actually, in this case, it is a spin connection. It is emitting infrared gravitons. No? So the infrared gravitons normally you don't care, but we already know from QED that if you don't care, you lose the fact that QED breaks Lorentz invariance.
It is a quantum effect.
It's a quantum effect. You will not see it classically.
Okay, what's the question?
So I got the concept of using asymptotically flat spacetime, but I'm not understanding the use of while algebra, which observables are actually corresponding to this effect. You're using while invariance.
While invariance.
You're using a while algebra.
Oh, that is to show you. Tell you, I was showing it for pedagogical. I have to show you how the calculations. Initially, I want to show you that this. So, what is the thing? This representation I get for quantum gravity is not a Fock space type representation, which you get by petimeter calculation. This is not that because of the infrared dressing. So, I want to show how that happens in a situation which you may more familiar, namely first quantum mechanics, where nothing great happens. Then in quantum field theory, where much great things happen, namely in the QED case, and now it is already happening in the quantum gravity case. So the quantum gravitational space cannot be quantized for the Fock space. That is the reason why the preliminary things on Weil's algebra was given. Also, it is culturally useful to know about Weil algebra. It's very important.
Okay.
One sub-question.
So that, no, because it will go up to, we have to go finish
Sir,
at
what is
1:30.
What is the reminiscent of the vacuum problem in gravity in the Weil formula?
What is it?
That a unique vacuum cannot be defined in gravity for field theory. What is the reminiscent of that problem in this formula?
That's what is the vacuum, is the ground state.
Ground state,
Yeah.
The standard ground state will not, no, it will be that, there is the point is that even for a massive particle in quantum field theory, because if there is a charged massive particle in quantum field theory, what will happen is that the ground state is not sharply separated from the mass shell hyperboloid. There is a whole continuous spectrum. So the whole character of the problem changes, including the fact, which I did not say, the mass shell of the proton is not sharp. The spin shell of the proton is not sharp. Okay? Muon decay lifetime does not transform from stationary frames to a moving frame in the formula which you are taught in elementary literature. It is not correct. There are corrections.
Okay.
So there are dramatic changes here and as well as here.
Bob, let's close for the